Hello, I'm Mayrin. Welcome to this video on finding the Higgs boson with only your mouse. For this video tutorial, we're going to be using 13 TeV ATLAS open data. ATLAS is the largest experiment on the CERN Large Hadron Collider, where protons get smashed together so that we can study what happens when protons smash together. And we're going to be sifting through the data that comes out of these collisions to find the Higgs boson. Okay, let's get started. The aim of this tutorial is to show you how to interact with particle physics histograms, and the first learning objective being to understand the principle of selection criteria, and the second being to understand the idea of signal and background. Now, some prerequisite knowledge is most useful to be able to follow this tutorial. Namely, on the LHC, its overview and research plans, and on ATLAS, how collisions are recorded and how particles are reconstructed. You can gain this prerequisite knowledge, for example, through this approximately 30-minute video tutorial series that you can find in the description. Here's a picture of a particle collision that we might be looking for. We have two beams of protons coming from the LHC along the right and along the left. And then in the collisions that we're interested in, Higgs bosons would be produced in the center, but they don't last for very long. So Higgs bosons decay almost immediately and they aren't seen directly in the detector. It's their decay products that are seen in the detector. Particles that we can see, which may be the decay products of Higgs bosons, are these red and green long lines, which could be muons or electrons, for example. We tend to call these collisions events in particle physics. Now let's talk about the Higgs boson decay that we're looking for. The signal that we're looking for is a Higgs boson decay to two W bosons, WW. Like I said, we're interested in collisions that produce a Higgs boson in the center of the detector, but a Higgs boson doesn't last for very long. It decays almost immediately. In the cases that we're interested in, two W bosons, a W plus and a W minus. W bosons also don't last for very long. And in what we're looking for, they decay, taking the W plus as the first example, into an E or mu plus and a neutrino. E or mu plus means a positron or an antimuon, but we tend to group together the positive versions and just say electrons for E minus and E plus, and muons for mu minus and mu plus. Similar for the W minus decay. In what we're interested in, it decays to an E or mu minus and a neutrino. So, opposite charge electrons or muons and two neutrinos. When looking for this signal, there are many processes that look similar to it in the detector. We call these backgrounds. The main background for this process is WW, which is exactly the same as Higgs to WW, except that the two W bosons don't come from a Higgs decay. They just come from something else in the collisions that has produced two W bosons directly from the proton-proton collision. The main difference between these two processes, Higgs WW and WW, is in some of the angular distributions between the electrons or muons and neutrinos. Another background is called TT bar. In this case, two top quarks are produced, top and anti-top, in a proton-proton collision, and top quark also doesn't last for very long. It decays to, in the case of a top quark, W plus and a B quark, and then the anti-top to a W minus and an anti-B quark. Same as before, the W bosons decay to E or mu and a neutrino, and same for the W minus. Now the main difference between this background TT bar and the signal Higgs to WW is that there are these two extra B quarks in the TT bar process. And we see quarks in the Atlas detector as what we call jets, and these two are specifically called B-tagged jets. Now, another background is Z boson decay, and particularly Z boson decay to an E or mu plus and an E or mu minus. The main difference between Z boson decay and the Higgs decay is that there are no neutrinos in the Z decay. And importantly, another thing is that the Z decay has to result in an E plus and an E minus, or mu plus and a mu minus. They have to be of the same flavor to conserve lepton number. This doesn't have to be the case for the Higgs to WW. We could have an E plus and a mu minus, for example. The particles that we can see in the detector are the ones whose lines end in these diagrams. So they are electrons and muons, B quarks, which we see as B jets, and neutrinos, which we see as missing transverse momentum, which we tend to call MET. So the presence of neutrinos gives a higher value of MET. Let's recap. The Higgs to WW process gives either 2 electrons, 2 muons, or 1 electron and 1 muon, plus MET from the neutrinos. Same for WW. Same for TT bar, but it also gives B jets. And the Z decay, crucially, different to the Higgs to WW in that it gives either 2 electrons or 2 muons. Can't be 1 electron and 1 muon. Okay, now let's analyze some histograms. We can go to this link, opendata.atlas.cern/release/2020/documentation to start analyzing some histograms. You're very welcome to pause this video and read through this website, but we're going to go straight to the data visualization page. And now please pause this video and read through these first pages on the Higgs boson, Atlas events, analyses, data and simulated data. And once you're done with that, go to the histogram analyzer simulation only page. So here is where the histograms will be analyzed. Let's scroll down to where they appear. They can take up to 30 seconds to load, so please be patient. And it's a really good idea to zoom out in your web browser until you can see all 9 histograms. So for me, this is Command minus and Command plus to zoom in. So you can see if I zoom in more, I can't see all 9 of them. So I'm going to zoom out to 67%. Here we are with the histogram analyzer. There are 9 different pictures here, and each of them is what we call a histogram. Let's concentrate on this one in the top left to explain what's going on. On the y-axis is number of events, and in this case on the x-axis is channel. So these are events or collisions that produce 2 electrons. There are about 3.3 million of those. In this bar, events that produce 2 muons. There are about 4 million of those. And in this bar, events that produce 1 electron or 1 muon. You can hover over this histogram to get a quick explanation of it. Now, the next one I'd like to point out is this one in the bottom right, where it tells you the expected number of events for 10 inverse femtobarn data. It says that we can expect 124 Higgs boson events. This many WW, this many TT bar, and this many Z events. Now, the number you need to keep in mind is this significance. A higher significance means you've done a better job at separating your signal from your background. You want to aim for as high a significance as possible. Notice that we start at 0.046. Now, one of the things I said that was different between the signal Higgs to WW and the background Z was that the Z can only decay to 2 electrons and 2 muons, but the signal Higgs to WW can decay to 1 electron or 1 muon. So let's make a selection to try and get rid of as much Z boson contribution as we can, because at the moment, all the histograms, all we can see is red, and that's from the Z contribution. So what we do is with our mouse, we drag a cursor over that bar to select only the E mu channel. And notice that the significance has increased to 0.333. So this was a good idea. The significance score has gone up. All right, something else that we said was different, this time between the signal Higgs to WW and the background TT bar, is that the background TT bar contains B-tagged jets. So let's choose B-tagged jets, no. Once again, the significance score has gone up. Another good choice. Another thing we said was different between the signal Higgs to WW and the Z was that there are no neutrinos produced in a Z decay to 2 leptons, which means it should have low missing transverse momentum in a Z decay. So let's choose events with greater than 20 or 30 in this case that I've done. You can try out different values of MET. That throws away some background Z, but keeps some signal. Now, your goal is to try and see some blue in these histograms. I can just about see some in the bottom left of this one, and you need to aim to be able to see more and more blue and thus increase this significance score. So we've got a challenge for you. It's to get as high a significance score as possible by playing with these 8 histograms, and then post your high score in the YouTube comments below. Now, I'm going to provide a few hints. If you want to reset your selections on all histograms, you can just reload the web page. If you want to reset on one histogram, you can click on the white area in that histogram. Like I said, you can hover over a particular histogram to get an explanation of it. If you scroll down this web page, there's an explanation of all of the 9 histograms, and you can get some hints that will help you in your quest to get as high a significance score as possible in these pages, separate signals and find the Higgs. There we go, let's go back here. Our challenge for you is to leave a YouTube comment like this, significance 0.461, that's the score I achieved. And that's it for the tutorial. Have fun rediscovering the Higgs boson with only your mouse. Hopefully, we have shown you how to interact with particle physics histograms, that you've learned to understand the principle of selection criteria and the idea of signal and background. Enjoy analyzing.